Well, I was going to try and get my cat to be on the mic, but she ran off. Hey, there you are. Say hi to everybody. Hi. Hi. Meow. 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 I gotta work. Yeah, my students are waiting for me. Sorry, Maya. I have no idea if you could hear my cat. I'll check the playback or something. I was also meowing in there, so I'm wearing headphones, so I can't really hear what she is doing. Welcome back to Chem 161. This is Thursday, week 3. We are going to finish chapter 2 today. That is the goal. In that, we are going to talk about the mole, how to calculate it, how to convert from grams to moles, etc. You will need a periodic table handy to get some numbers off of it so that we can calculate molar masses and stuff like that. Oh, you only heard me meowing. That's sad. Okay. Well, you can imagine what she sounds like, I guess. I do have, like, the ultra-fast mode on. Ultra-fast in air quotes here. So there should be less delay between you typing and me answering. But if there are issues with the stream, let me know. I can always change it back. I know one student yesterday in my evening lecture seemed to have an issue with it buffering constantly, but everybody else's was fine. So I don't know 100% if this mode is worth sticking to or having the 20-second delay and making sure everybody can access it. So I'm going to play around with it some more. We're going to use it for today, and we'll see what happens. So let's talk about how you manipulate chemical formulas and get useful information out of them. The first thing we're going to talk about is how do you draw a molecule. There are a whole bunch of different ways to do it, and we're going to do a few of those in this course, particularly these two right here. So this one, the molecular formula, and then also the structural formula. This is what's known as a Lewis structure. And later on in the quarter, you're going to be asked to draw Lewis structures of various molecules. This shows how the atoms are connected. The lines that are drawn between the atoms indicate covalent bonds, which are bonds that are very strong and hold the connected atoms together, kind of like if they were roped together or tethered in some way. Geometry is very important, so what we're going to need to do is not just consider them in two-dimensional space, because this guy is 2D. Over here, this guy is in 3D. And that helps us learn a little bit about how molecules behave, because their shape dictates what they can interact with. For example, if you are looking at a jigsaw puzzle, you can only put certain pieces together because their shapes match. With molecules, it's the same thing. Enzymes will only accept certain shaped molecules, and something that is a tetrahedron like this molecule would not fit in a slot that is flat for, say, a ring. And then we have the space-filling model, which we're not really going to do much with this in this quarter. This does become important in organic chemistry, and we do touch on it very briefly in Chapter 5 at the very end of the quarter. Down here I have this molecule, oops, that's not the letter S, that's number 8. I have S8, which I just realized is written over here. S8 is a cyclic ring-like structure, and if you drew it on this map right here as a two-dimensional octagon, you might believe that, oh, okay, this is a perfectly flat thing, and I could, if it was a frisbee, I could throw it. But in reality, what ends up happening is it goes up and down, and up and down, and up and down, and up and down, and it's every other one alternates, and it gives you this sort of puckered shape. The reasons for that we'll talk about in Chapter 4 when we talk about geometry, but the 2D representation is often misleading, and the 3D representation is much more important. So something to keep in mind that when we start looking at molecules, when we get to Chapter 4 and we begin to draw them on paper, what you draw is not necessarily what it is, because three-dimensional molecules exist, and there are specific geometry rules that we're going to have to follow. This is a disambiguation slide. What that means is that there are many ways to put the letter H and a 2 around it, and they all mean different things. So on this slide here, I have both letters, which are my element symbols, and then I have numbers, which, depending on where you put them, mean different things. The important information here is that a coefficient that is in the front affects the quantity of how many things you have. But the subscript is used in cases where you have multiple atoms bonded together. So if I say 2H, I have 2 individual H's. If I say H2, I have an H2, and those H's are stuck. They're stuck together by a bond. If I have 2H2, then I have 2 groups of 2. Later on, when we're going to count how many atoms are in like a chemical equation, to get the total number of atoms of, say, hydrogen here, I would have to multiply these guys together to get the quantity, because there are 2 groups of 2. So when you are writing stuff on your paper, make sure that you are notating it correctly, because if you meant to put H2 and you put 2H, those are very different things to a chemist. And one of those will be extremely reactive, and the other one will be sort of reactive. Which one's which, we'll get to that as the quarter progresses. When we represent molecules on paper, describing their nature in reality is very important. However, there are certain elements that tend to pair up, and this is due to their reactivity. They react very strongly with each other. For example, nitrogen atom by itself is very, very reactive, and it will immediately combine with other nitrogen atoms. There are 7 elements in nature that tend to do this. I've written their formula as a generic E2. These are diatomic molecules, which means they occur in pairs. And I call them the silly 7. And I don't know if I've seen this name anywhere else. But the 7 molecules that you want are right here. So they're these guys. And then hydrogen. And you'll notice that the shape that they make on the periodic table is a 7. And also that the stem of the 7 is in group 7A. And then why is hydrogen over here? Well, that's because he's silly. And so that's the silly 7. So these 7 elements always exist as diatomic pairs. And that is something that is worth committing to memory, in case you get questions that ask you, like, oxygen gas reacts with hydrogen gas, what is the product? And if you said O plus H equals whatever, you would actually get the wrong answer. And again, H is silly. That's why he didn't join the party. The next thing we're going to talk about is the empirical formula. An empirical formula is like a written formula or structural formula that you'd like, say, CH4 or whatever, but there is a special rule for empirical formulas, and that is that they occupy the simplest ratio of atoms possible. For instance, if I gave you this molecule right here, this would not be an empirical formula because there is a number that I can divide out of both sides, and that number is 2. This, however, would be an empirical formula. I wrote over my text. Oops. Hold on. So let me clear that out of the way. Boop. So if I gave you this molecule, C6H6, and I said, what is its empirical formula? First thing you want to do, you want to look at the formula and determine, is there any number that you can divide out of that formula? Very obviously, since they have the same number, I would divide that out, and the answer that I would get would be this. So the empirical formula of benzene would be CH. Now, if I give you something like this, it's a little more complicated. So it becomes a hunt for the greatest common factor. And sometimes you will end up in situations where there just isn't one, even though none of the numbers are 1. So something like C2H3 is an empirical formula. But C2H4 would not be, because you could divide out the 2. We can only ever have whole numbers for our empirical formula. And so for this one, and people are already typing in the answers, so that's good. It means that the ultra-fast setting is working. In this case, I would also divide out 6, so I'd get CH2O as my answer, because each of those numbers is divisible by 6. You could also divide by 2, which would then get you like C3H6O3, and you'd probably realize after that, oh, I have to divide out another 3. And you just keep doing this until you get the simplest formula. Lastly, if you already have the simplest formula, and there is no common factor that you can divide out, then that is the empirical formula. So some molecules are their own empirical formulas. Now, why do we care about what an empirical formula is? I don't honestly remember if this slide is coming up or not. Let me see if it... No, we're going to talk about isomerism. This might come up on a later slide. But because I have a picture here, and there's the definition right there on the screen, so that's fine. Let's suppose that I had a molecule, and I didn't really know what its identity was, but I knew that it contained carbon, and it contained oxygen. And so what I do is I go to my mass spectrometer, and I start weighing stuff. Now, I can't just split up one molecule. What I end up doing is splitting up tons and tons of molecules. And after a while, I will accumulate a pile of them. So let's suppose that this is my pile, and that for carbon, I notice that this is what my output is. And then for oxygen, I get this instead. I gotta make sure I counted this correctly. There we go. So this is our output. Now, because we can't split one molecule, in fact, each of these dots would probably represent like a trillion molecules, or a trillion atoms of carbon in this case. What we would notice is that there is some amount of C, but there is twice as much oxygen. And so what we would conclude is that our molecule has the empirical formula of CO2. Now, does that mean that this is CO2? It turns out it doesn't, because any of the... Oops, I'm drawing on my layer again. That's okay. It turns out that any of these molecules could be possible. So it could be this, but it could also be this molecule, because this molecule would have the same ratio. It could be this one. Any of these are possible. Could it be this one? Turns out it can't be that one. So we learned something based on what ratios are possible when we write out the formulas, and also what our outcome is. So the empirical formula helps us get closer to figuring out what something is. The last step is to weigh it on the mass spectrometer, because we know what carbon weighs. We know it weighs 12, because that's our definition. And then you can weigh anything relative to that. So once you figure out the empirical formula, you can then weigh your product and figure out what multiplier it is to get its actual formula. And that's how we got all chemical formulas today. To round off this last little bit about what molecules and their structures and shapes and how we work with them are, is a topic about isomerism. there are many different ways to write a molecule on paper, and some of those are ambiguous. For example, if I give you this formula, C2H4O2, and ask you to draw all the bonds between the atoms, you could come up with two different possible answers. In fact, you could come up with all sorts of different possible answers. Some of them would be invalid because there are certain rules for drawing Lewis structures, but these two structures both actually exist. On the left is acetic acid, on the right is methyl formate. One of these is used for cooking, the other one is toxic. Choose wisely. This one over here on the left, this is the safe one. Acetic acid is vinegar. This one on the right is very, very bad. And the only thing that we did was we swapped these two atoms' positions, and this double bond O sticks along with the C. So an isomer is any structure that has the same molecular formula, but a different connectivity in space. And so the change is this region right here. And that's all it takes. You just switch those two spots, and then suddenly it's toxic. Now, this has to go back to why does this happen? This has to go back to where we talked about shape. So this molecular shape, and also the fact that these atoms that are all connected together, this C and these O's, have a special property called acidity, and we'll talk about that in 163. But this molecule has a very different shape. It is not acidic. Trying to think of what I can really say about this. So it's very polar. It is an aldehyde, which is also kind of reactive on its own. Just generally bad for you. I can't really say much about methyl formate because I haven't studied it. There are many other types of isomers out there. This is the first type. These are structural isomers where they just have a different structure. But some molecules can have the same formula and the same structure and still be different. And you might be asking yourself, well, how the hell is that possible? And the answer that I have for that is to take your hands. So now I'm imagining all my students taking their hands and holding them up in front of the computer. Now look at your hands. Do your hands have the same structure? And the answer is yes, because your palm and all the muscles in there connect to your thumb, and then your thumb is off on its own, and then your fingers are in where their locations are. But if you try and superimpose your hands by putting one hand over the other, you'll notice that they're not the same. One will be facing up and the other will be facing down so that your fingers and thumb match up. And this is called a spatial isomer. Spatial isomers have a mirror image property to them, in which case they are the same, but only if you reflect them through a mirror, and your hands have this property. This is a property called chirality. We'll write that on the screen here if I can get the pen. Something that is chiral means that the only way to have the same structure but different actual physical presence is to take its mirror image. In this picture here, I have indicated a CH bond that is different in both of these structures. And it's really hard to tell on this picture, and I'm trying to find where specifically it is so that I can point it out to you. So here is my CH bond, and it's pointing back in this diagram. And in this diagram, it's also pointing back. But if I were to rotate this around 180 degrees, it would then be pointing up. So that's what they've done over here. Oh, actually, they did it in the reverse. So here is this guy. But now on this diagram, there it is right there. So for this specific molecule, on the left is caraway, and on the right is spearmint. And all it does is that little tiny flip means that you taste something totally different. I actually don't know what caraway tastes like. I know what spearmint tastes like, but these molecules, to my understanding, are quite different. And the only difference is just where that H is connected in space. So structural isomers exist. Spatial isomers exist with chirality. Are there other isomers? Of course there are. But we're going to save some of those isomers for you when we get to organic chemistry. You can talk about cis-trans isomerism. You can talk about... I'm coming up with a blank. I don't teach organic that much, so... Caraway's like licorice. Oh, okay, then I probably have had that. I really don't like licorice. I find it weird, and I don't know why. Alright, so let's talk about how we actually count all these molecules and atoms, and that's where the mole comes in. If you have taken Chem 140 or chemistry in high school, you have seen this quantity. This is Avogadro's number. So if you're looking for someone to call to ask questions, you just dial 6.022 times 10 to the 23 in your phone or calculator or whatever, and then the operator will be like, what the hell is wrong with you? Avogadro's been dead for years. Avogadro is a guy who did a lot of experiments with gases, and he determined this fixed quantity, which he called the mole, to contain this number of things. And that number is 6.022 times 10 to the 23, which is a humongous, humongous number. But that's the number that we use, and the reason for that is because this quantity, the mole, represents a reasonable amount of substance that we will work with. Now, by definition, since we've been using carbon-12 as our weight measure, we're going to also use it as our mole measure. And so 1 mole of carbon-12 ends up being exactly 12 grams of carbon. Now, this relationship is exact with this one. However, as you could probably guess, this number in the middle is not exact. Because there's no way that we would know the next 17 or 18 digits down to the precise atom. I believe that Avogadro's number has been solved down to like 6 or 7 numbers, but it is very difficult to go any further than that. Since we have all these relationships, we can do conversions just like we were doing in Chapter 1. And that's actually the point of what we're going to do today, and also of lab worksheet number 2. So let's do some calculations using these types of relationships. That's actually more digits than I thought it went to. I only knew up to the 5 in that. So I knew the 6.02215, but I had no idea. There isn't a 5 in that, but the 4. Okay, I just didn't know, I guess. That's not the right thing. I want the pen here. This is what I want. Okay. These relationships that I'm highlighting in yellow are going to be very useful to us, and I'm going to highlight another one in a different color. This one's not super useful, but you can have it handy in the event that you need to convert directly from grams to particles. And the reason that it's not super useful is because oftentimes we want to turn stuff into moles, and the mole is going to be our bridging unit. We're going to connect moles to other things. So turning something directly from grams to, say, atoms isn't very helpful, except in specific cases. Now, obviously, I'm not going to be over your shoulder telling you, you should convert to moles, you should convert to moles. But I would personally convert everything to moles for every calculation, even if it invokes a second step. And that's what I'm going to do on my slides here when we do these problems. Now, this is carbon. What do you do if you want to do, say, like iron or oxygen or fluorine or whatever? It turns out that the number that is used, that 12 grams of carbon-12, is just the formula mass of whatever molecule you're working with, or the atomic mass of whatever atom you're working with. So, on the periodic table, all of the masses that are listed at the bottom of each cell for all of the elements, those are what are known as molar masses, and those are the mass of 1 mole of an element in grams. So, for example, if I gave you iron, what would its molar mass be? So you got to find iron on the periodic table. Iron is Fe. It's number 26. I think what you have on the chat is number 9. That's fluorine. So if I asked you, how much does 1 mole of iron weigh in grams, it would be this many grams, because that is the number on the periodic table. Your periodic table may have less or more significant figures. Whenever you are using a periodic table value, write down all the numbers that it gives you and use them all as sig figs. Some elements are known to an absurd number of sig figs, depending on what source you're looking at. Like, I think aluminum is known to like 7 or 8 sig figs. And some elements just aren't. For example, lead only goes to the 10th place. All of the numbers should have at least 4 sig figs, but just use as many as you have, and then it won't be the limiting factor. That's my philosophy when doing these problems. If you have a molecule, all you need to do is add the atoms together in terms of their formula masses. That will give you the molar mass of the substance. For instance, if I wanted to figure out the molar mass of sodium chloride, I would look at the periodic table and say, oh, okay, well, sodium is 22.990 grams per mole. Chlorine is 35.45, and I don't know the last number, 3 grams per mole. And so I would just add those together using the rules for addition to figure out my significant figures. And this will be in grams per mole. And there you go. So this should be 58.443. My answer on the screen is using a periodic table that only had 2 decimal places. Yeah, why is that? If you look at the periodic table, you'll see that technetium's 98. But it's in brackets. Or at least it is in my periodic table. Some of the numbers have a special designator where they're just integer numbers, but they have like a brackets or carets around it or something. And that's correct. It's because they're radioactive. Radioactive atoms are unstable, and that means that weighing them is difficult because their weight changes. And so we can't report that number. Let's suppose that you had this molecule, and I asked you, hey, find the molar mass of C6H12O6. Now, you could do this sort of thing. I'm going to show you the long way, and then I'm going to show you the much, much easier way. So let me go back here. I need to... Oh, it's already open, so I just got to... I ruined my layer. Hold on. Boop. Boop. And then I got to come over here. There you go. So yeah, you are already getting the answer, but here's how you do it on paper, which this is going to be really obnoxious. So oh, I thought it was going to work. Okay. Well, I don't know what's wrong with my undo button on my tablet. Sometimes it works and sometimes it doesn't. So what I would do is I'd say, okay, 6 times 12.011 grams per mole, 12 times 1.0079 on my periodic table, and so what I would have to do in order to solve this is that I would have to do this multiplication. It turns out these numbers are exact because they're counted. So I would get this number sig figs. And then I would have to do addition and do sig figs that way. And you're going to end up getting an answer that you would report to the thousandths place. And whatever the answer ends up being, and I believe it's 180.156. So that's like a 3-minute ordeal just to figure out the molar mass of something every time. And you might just say, that's dumb for something so easy. I don't want to deal with all the sig figs. I don't want to deal with all of that nonsense. There's got to be a better way. And it turns out that with this one trick, doctors and PhD students everywhere hate it. You can find the molar mass of everything by going to this website. I'm trying to type it in while I'm talking. Give me a second. Molar mass calculator. Okay, so if I go to Google, and it's not showing my window here. There we go. So if you type in Lentech molar mass calculator, which I believe is just hiding off the top there. There we go. And you click on this link. Then you get a website that looks like this, and half of the window is covered by chat. So let me do this. I'll just put the part that we need here. And so now what you can do is you could just type in any compound. C6H12O6. Hit enter. And there you go. That is the formula. 180.16 is the molar mass. And you're all set. So the only downside to using online calculators is that they only go to the hundredths place. But if you are using a number with 5 sig figs, then you're going to be fine in your calculation. You just don't want to use a number that only has 2 sig figs or 3 sig figs or something like that. And generally speaking, as long as you aren't just typing in like H, that won't happen. So you could do any compound you want. So I could be like PB3N2O5, and there you go. It's all set. Okay, so that's Lentech. That has been around forever. Apparently, it's a water treatment company that has a molecular weight calculator. I don't know, but it was the first one that came up. I've been using it ever since. It's never failed me. So that's not the slide. There we go. Finally, we can do some calculations using the mole. And the way that we're going to do that is to either invoke Avogadro's number, if we need to turn something from count to moles. And so when I say count, I mean how many particles are present in the sample. So that could be atoms or molecules or ions or whatever. Using the molar mass from Lentech or the periodic table or wherever, we can turn mass into moles, which means that we can turn particles into grams by turning something into moles, because these two are the same thing. So let's do some of that. Let's do some calculations to practice this concept, because we will need to be experts at it in order to be successful in Chem 162, really. You're going to do very little stoichiometry in this class, just in the lab stuff mostly, and in this chapter, of course. Minimize. There we go. Boop. Boop. All right, so how many moles of silver are there in 154.1 grams of it? So I have this quantity, and I want to figure out how many grams of silver turns into how many moles of silver. So just like before, when we were doing unit conversion, you could set up your little chart, your little blueprint here, and figure out, how do I get from the start to the finish? And so if that writing out all the units helps you, please make sure that you do that. I know the relationship between grams and moles because there is a relationship on the periodic table. 1 mole of silver is, according to the periodic table, 107.87 grams. I've connected my units, I've linked them, so now I will do the dimensional analysis. I don't want this unit. I'm going to turn it into this unit. These cancel. This is the target unit. Therefore, when I run the numbers, that will be what my answer is. So I write in the numbers, and I just punch it in the calculator, which, of course, is sitting in the corner of my desk. I got to reach it. 154.1, 107.87. And I got 1.42857, 1429. How many sig figs do I get to keep for my answer? Looks like I get to keep 4. So I would report 1.429 moles of silver. So that's just a simple calculation that we can do. Let's do another one. How many atoms of silver are there in this sample? So we'll just scroll down a little bit, make some space. So this time what I want to do is I want to turn grams of silver into atoms of silver. Do I have a conversion that you can use to go directly there? Yeah, it's the weird one where you just take grams and Avogadro's number. But it's much better to get into the practice of just turning everything into moles because you're going to do it so often. So I'm going to show it that way. So I know the relationship between grams and moles. So this is 107.87. And 1 mole of silver, the same as 1 mole of anything, is going to be Avogadro's number of silver. I had to cram that in the corner there. I'm sorry if it... Oh, it did fit on the screen. There we go. So let's solve the problem. You guys have already solved the problem for me. So that's good. I don't remember what we're starting with. 392.5 grams of silver. But yeah, if you know how to do this, like, go for it. Grams of silver we don't want. We're going to turn that into moles of silver. Moles of silver we also don't want. We're going to turn that into atoms of silver. And then we'll fill in the numbers. And then we'll fill in these numbers too. And I should just trust that you're right, but I'm going to punch it in the calculator anyway. .191 times 10 to the 24. That should be a G. There we go. So why is it 10 to the 24, not 10 to the 23? My best guess is that when you divide... Let me get a different color out here. When you divide these two numbers, this number right here and this number right here, you get a number that's about 10. And then 10 times 6.022 times 10 to the 23 would be 6.022 times 10 to the 24. So it's just affected by the magnitude of the numbers that are left over. In fact, dividing those two numbers gets you about 4. So 4 times 6 times 10 to the 23 would be 24 times 10 to the 23. Or 2.4 times 10 to the 24, which is roughly what our answer is. So the magnitude will increase based on the magnitude of the numbers that aren't Avogadro's number. All right, you guys are experts, so let's do more complicated examples here. How many molecules are in the sample? I'll give you 2 or 3 minutes to tell me the answer, and then I will calculate the result alongside you. So let me turn on my phone stopwatch. Go ahead and type in the answer when you think you got it. And I'll be back to check up on you in just a second. All right, hopefully people are most of the way through the calculation. Let's go over the problem. I gotta clear my canvas here. Does that actually get everything? I think so. That's a really helpful preview. Thanks, PowerPoint. Hold on. All right. Do I still have Lentech open? I do. Okay, so C4H10. 58.12 is what I got there. So that'll be good enough for our work. So I want molecules present in grams. So I have grams of C4H10. And I want molecules of C4H10. So I know the relationship between grams and moles, it's just this right here. So this would be 1 mole of C4H10. And then moles to molecules, 1 mole of anything is 6.022 times 10 to the 23. These aren't actually atoms, so I don't want to write that. So let's set up the calculation. I have 9.213 grams of C4H10. And I want to turn grams of C4H10 into moles. You'll notice that I'm writing the C4H10 every time. And the reason that I am doing that is because later on we're going to turn moles of something into moles of something else. And if you just write moles, 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 moles all over the place, you won't know which one is which. So having this little indicator that tells you what it is that you're working with is super useful. And this will be moles of C4H10. And this will be molecules. Oh, I had to write over myself. That's unfortunate. So now I can fill in the numbers. There is 58.12 grams in a mole of this stuff. And then in 1 mole, there are Avogadro's number. I apologize for that getting crowded up there. So there will be this many molecules, which it sounds like everybody is getting the same answer. So that is good. 9.213 times 6.022 times 10 to the 23rd divided by 58.12. 9.546 times 10 to the 22. That should be a 2. There you go. Now I see that in the chat everybody was getting 9.545. That's also correct. Remember that the last digit is estimated or closely known, but it is not exact. So if you're off by 1 in the last digit from my answer, I mark it right. All you have to do is be close. All right, so for the next question, which I'm just going to leave this on screen here. We'll just go straight to it. In this sample, how many hydrogen atoms are present? So what we can do is we can do an extra little trick here. So I'm going to scroll this down. And this is something that we're going to learn a little bit more about in 162 when we do stoichiometry. But what I can say here is if I wanted to figure out how many hydrogen atoms are in the sample, well, I could say that in 1 molecule, of C4H10, how many H's are there? Well, there it is right there. It's that. So there must be 10 atoms of hydrogen. So what that means is I can take the number from the previous problem I can do more stoichiometry with it and say that in one molecule of this, there are 10 atoms of H, and then I just get the above number times 10. And so if I want to calculate parts of a molecule, I can use the formula to make another relationship. So any relationships that you make are valid can be used from any point in your answer. That might be it. That might be all of the slides. Yeah, that is the last slide. Okay. So, sweet, we're ahead of schedule. So I'm going to put these slides on the board. I want you to try these problems. This third problem is actually the challenge problem. This one right here. So I'll give you about 7 or 8 minutes to try and do these. And then we're going to go over the answers. And then we're done with Chapter 2. We'll take a break and we'll come back and do Chapter 6 so that you get to see what molarity is fairly soon. All right, I'll see you in a bit. Good luck. We're all counting on you. We'll go over the answers shortly. So about 1 more minute to finish your problems. Oh, I didn't clear my canvas here. Oops, scrolled too far. So I'm going to solve these without doing the little, like, unit map, just because I don't want you to have to sit through 10 minutes of explanations. But we want to know the number of moles of helium in the balloon here. I can turn grams into moles. And it's like 4 something. I got to look at the number. 4.0026 on my periodic table here. So whatever 19 divided by 4 is. 4.846849. I have 3 sig figs, so I get to keep 3. 4.85 moles of helium. So that's the first one. How many atoms of sodium do you get to have per day? Well, let's find out. First thing to note is that this is in... Why is it on cut? There we go. Okay. First thing to note is that this is in milligrams. So that's not going to be super helpful to us when we solve this problem. So the first thing we got to do is turn it from milligrams to grams. And then once I know grams of sodium, I can do moles of sodium. And once I know moles of sodium, I can do atoms of sodium. So that's the relationship between milligrams and grams. 1 mole of sodium is 22.99. 0. And then a mole of sodium is 6.022 times 10 to the 23rd. And I got 6.3 times 10 to the 22 atoms of sodium. I only get 2 sig figs because this number right here is 2 sig figs. So be mindful of that. Just make sure I did that right. Sometimes you're going to get these weird problems where I ask you questions about geometry. Like, I might give you the formula for a cone and be like, here's this solid gold cone. Tell me how tall it is if it has this many atoms, or something like that. And this is one of those problems. So, in this problem, I need to know the radius of the sphere, which means that I need to know the volume of the sphere, which means that I need to know the mass of the sphere, and I am given the amount of aluminum I have. So this one, it might be worthwhile to show the unit map here. So if I do atoms of aluminum, I can turn that into moles of aluminum, which I can turn into grams of aluminum. Then using the density, you can get the volume of the aluminum. And then using the formula, you can turn it into the radius of a sphere. And it should be a tiny sphere, so if you're getting a small number, that's probably correct. Now, when you're doing the unit map, you can't always do that in one-dimensional analysis formula, because formulas exist down here for this. So this is going to be V equals, is it 4/3? Yeah, 4/3 pi r cubed. So once we get an answer for the volume, we can just plug it into that formula. So atoms to moles. I'm going to run out of space again, so I'm going to just go to the next line here. Moles to grams. And then grams to cubic centimeters. All right, so in a mole of oops, no, that's right. In a mole of aluminum, there are Avogadro's number of atoms. And then in a mole of aluminum, there are how many grams? 26.982. And then in a mole, or in a cubic centimeter of aluminum, there are 2.70 grams of aluminum. So that's going to give me an answer in cubic centimeters of aluminum. I got 1.42 cubic centimeters. So this is like the tiniest sphere. So if this is the volume, and I want to solve for the radius down here, let's solve for r. And so that's going to be V equals 4/3 pi r cubed. So I'm going to take that. I'm going to multiply by the inverse to get 3/4, and then divide by pi. And then I will cubed root that. And that's r. Now, there's cleaner ways to do this. I could write 3v over 4 pi. But what's important is it gets in your calculator the right way. So whatever the volume was, 1.42 times 3/4 divided by pi. Do I have pi on my calculator? There it is. And then cubed root. Remember, if you don't have a cubed root function on your calculator, doing this is the same as this. And everybody has an exponent function. You could just do exponent 1/3. And I got 0.697. I put in V in cubic centimeters. The cubed root of cubic centimeters is just centimeters. There is the radius of the sphere. All right. One more problem, we'll take a break. Can't read the denominator. Oh, this right here? Sorry, that's supposed to be pi. So this right here. This is that's times. That's my calculator, or my handwriting not being great. So this is times. And then that on the bottom is pi. Sorry, when I push my pen on the screen, and if I push it hard enough, I get a dot. But if I tap it really briefly, I don't always get something. Now I'm getting dots all over the place. Can I write how I plug in the calculator? Sure. So what I did was I wrote this. So on the calculator, I wrote 1.42. And you can see that I missed my decimal point there. Times, parentheses, 3 over 4. Parentheses, divided by pi. Parentheses, caret, 1 over 3. So that's what my calculator input looks like, although I did it across multiple lines, which is why I went back and put the parentheses. And you could also do 1.42 times 3 divided by parentheses 4 times pi. Probably the biggest issue is going to be, did you put a bunch of parentheses when you're typing it in your calculator? Because what your calculator tries to do is it tries to do multiplication and division in the order that it sees. So if you type in this, what it's going to do is it's going to do this, and then it's going to do that, and then it's going to do that. And you can clearly see that one of those is not necessarily correct in all cases. So put abundant parentheses, and you'll be all set. All right, one more problem. How much space do I have on this? I have plenty of space. Okay. All right, so I'm going to take my 500 milligram sample of ibuprofen. And it wants to ask how many molecules there are, so I'm going to turn first my milligrams into grams. And IBU is going to be my abbreviation for ibuprofen. Then I can take grams of ibuprofen into moles of ibuprofen. And then I can take moles of ibuprofen and turn that into molecules of ibuprofen. (10 to the minus 3). Let me look up the number for Lentec. This is probably like 180-ish or something. Where is my Lentec? There it is. C13H18O2. 206.28. Sorry, I see things in the chat. I'll get back to that in just a second. And then in a mole, there are Avogadro's number. That should be a decimal right there. All right, so I have 500 times 10 to the minus 3 times Avogadro 206.28. And I got 1.45967 times 10 to the 21. How many do I get? I get to keep 4. 1.460 times 10 to the 21. All right, so we got that. And then the next question asks you, how many carbon atoms do you have? Well, I know that in a molecule of ibuprofen, there are a specific number of carbon atoms, and that number is 13. So I'll just times these together. And I get 1.8. Oops, not 1.8. 1.90. It is 1.8. I get 4 sig figs. Hold on. There you go. Yeah, it's a conversion. There are 10 to the minus 3 grams in a milligram. Can you post practice problems like that one? There are problems in the textbook, so use the end of the chapter 2 problems. There are plenty for you to try. Looks like everything else is good. Those are the answers. We're going to take a short break. I mean, we're going to take the same break we take every time. I don't know if my timer... Well, my timer is right here. There it is. Oh, that was my Zelda randomizer time. So we're not going to play for... We're not going to take a 3-hour break. So let me clear that. Oh, shoot. I forgot that I had broken the timer. There we go. All right. Now we'll take a 10-minute break. So I'll see you after that. Oops, I'm sitting here browsing my phone. Boop, boop, boop. All right, so that should be everything. Oh, I got to get the timer out of the way here. Hold on. Oh, I forgot that I have like little sound effects in here. I need to actually hit mute for that. All right, so let's summarize what we did in Chapter 2 before we start Chapter 6. At the start of Chapter 2, we went over the history of the atom. We talked about how the concept of the atom came about from Democritus, how Dalton refined that and talked about, oh, here's how atoms rearrange, here's what I predict that they will be, and then how later experiments refined those ideas even further to give an idea of what was inside the atom, the proton, the neutron, and the electron, and also how isotopes affect different masses of different atoms. So, for these two things, what I want you to know, most importantly, is that you want to know the postulates of Dalton's atomic theory, and then this right here, which will require you to use the two above things. And we went over how to do that in class, where you look at some numbers and then you say, oh, okay, are these the same compound or not? That's something that I'm going to ask you to do. Down here, this is important too. You're going to have to know these experiments. So you got to know what a cathode ray tube experiment is. You got to know what the oil drop experiment is. You got to know what Rutherford's experiment was. And tell me, like, what they showed. And then, of course, you got to tell me all about the proton, neutron, and electron. Wow, that was a terrible... My hand got caught on my paper, that's all. And then also describe the atom structure. Finally, talk a little bit about isotopes and just know what the difference is between an isotope and something that is just two different atoms. For the next section, we had you just do like ZAE symbols and notation. Basically, a bunch of simple contextual stuff on the periodic table that we went over pretty quickly on Tuesday. So be able to determine all the relationships between protons, neutrons, and electrons, what the numbers on the periodic table mean, and so on and so forth. And then finally, all of the calculations that we did today. Make sure that you are able to convert from grams to moles. Make sure you can convert from particles to moles. Make sure you can determine the formulas of compounds and also do the calculations similar to those that we did today. The one that I showed you with the aluminum sphere is the hardest type of calculation I can give you. I might give you a geometric shape. I might give you something simpler or more complex, but I will always give you the formula. But the execution of the problem is very similar to what we just did today. It's just, can you find a link from what you're given to start to the other end of the problem? And if I give you one end of the problem, you should be able to go the other direction. For example, if I gave you that radius of an aluminum sphere today, you should be able to turn that into a volume, then use the density to turn it into a mass, and then tell me the number of atoms that are in it. That's Chapter 2. The screen should go blank when I hit the button here. And nothing should appear because it hasn't captured anything, because I got to close this window to open Chapter 6. And I need just a second here. So we don't do the chapters in order. We're going to do Chapter 6 next. So if I do this, it should now capture. Okay. And it did. Okay, cool. Chapter 6 starts with what's in 161 live, I would call a warning. But given how much awfulness has happened with the whole pandemic and everything, we're not going to be memorizing polyatomic ions because you're going to just have an assessment and then you just have this chart handy with you. So it says here you must memorize this list of polyatomic ions, and there are a lot of polyatomic ions. I'm not going to make you memorize it because I have no way of doing that. I'm not going to be like calling you up at 3 in the morning and be like, all right, you have 10 seconds. What is phosphite? And then if you don't know the answer, I drop you from the class or something like that. This is not going to be that extreme. But that being said, when you get to 162, other instructors may have the expectation that you do know these and have committed them to memory. So it would behoove you to learn them. Okay. The chart is in the OpenStax textbook on these pages. I have also provided you with extra ones that I like for my students to know because they're similar enough to ones that exist that committing them to memory is not all that difficult. Here's the list. I'm not going to have these on the screen for very long, but if you're watching this video in the future, hi from the past, you could pause the video. If you have your slides handy, this is one of the first few slides in Chapter 6, so you can just look at those. This is page 1. This is page 2. Anything with an asterisk is not in your textbook, but I encourage you to learn them. And there are some hints for memorizing them if you choose to do that. I'm not going to really spend much time on that, just because we aren't going to memorize them in this class. I'm not going to expect that of you for this quarter. Okay, so Chapter 6 is not very long. You'll notice there is a little bit about balancing chemical equations at the end. I'm actually going to skip that because you'll do that in 162. In the past, I believe, like, we were asked, hey, can you do balancing equations? And then we realized, oh, we just do it again in the future anyway. So I'm going to just do the stuff in Chapter 6, which makes Chapter 6 nice and short. We will probably finish this, I'm going to say Thursday next week, and then we're going to start Hell. Hell being Chapter 3. Chapter 3 is where shit gets real. Yes, I'm going to commit that to YouTube. Chapter 3 is where shit gets real. Chapter 6, however, is a lot more review from the past, so let's do a little bit more review. So how do I determine how much stuff is in a compound by percentage? And the way that you do that is to do this formula. This is the formula for percent composition. If I know the mass of something, and I know the mass of what that something is in, I can take a percentage. That's really easy. So if X is some element, and I know what it weighs, I just divide it by the mass of everything. And that's the percent that is X, or whatever it is you're looking for. Let me put that formula back up for a second in case you want to copy that down. We're going to use this specific formula in several permutations. And what's going to end up changing in each of these permutations is this right here. We're going to just change this thing at the end. Instead of multiplying by 100%, we're going to times it by something else. Alright, so let's do an example. I have a mineral, and the mineral has this much iron, this much sulfur, and this much oxygen. What is the percent composition of the mineral? Well, if I can find my cursor, I'll get back to this. There we go. Oh. The most helpful preview. Alright. So, the formula for mass percent, or percent whatever X is mass X mass total times 100%. So in order to do this, I'm going to need to know the total mass. So right off the bat, we should just do that. 15.9 plus 26.8 plus 17.4. And the number my calculator spit out was 60.1 grams. And so now I can do each of these percentages in turn. So percent iron would be the mass of iron divided by the total mass. And when I punched that in the calculator, I got 0.2645, times 100% is 26.5%. I can then do the same thing for sulfur, which would be 26.8 divided by 60.1. Those are both in grams. Those go away. And then similarly for the oxygen, I get... Oops, I hit the wrong button. 29.0. That's not a very good sigma. That's supposed to be a sum. There we go. If I were to add all of these things together, so this 26.5 plus 44.6 plus 29.0, I wonder what number I should get. And because of a little bit of rounding error, that's how rounding works. You always round up on 5, so you're going to have a little bit of bias towards a higher answer. If I sum them all together, I get 100%. That is close enough for government work. So this formula has worked and done what we wanted it to do. For the next problem that I have here, we can figure out... Oh, I didn't actually hit the space bar here. There we go. This problem asks... Well, I have the answers on the screen. I'll just do this. What is the percent composition of aspartame? And you might be asking yourself, well, what mass do I have? Where's the mass total? And the answer to that is, well, you have a mass total. It's the molar mass, right? Sorry, I gotta scroll around here. So if I go to Lentech, and I get the mass, (294.30) is the mass total. I've already forgotten it. Good job, me. Where did it go? There it is. 294.30. So if I had 1 mole of stuff, and I wanted to say, okay, I want to figure out what the percent composition of that is, that would be a 294.30 gram sample. So let's figure out the mass percent of carbon, which would be whatever carbon weighs times how many there are, because if there's 14 of them, that's going to be a much larger part of the sample than if there was 1. The grams per mole cancel out, and I get a headache because I keep hitting the wrong buttons. 57 point... I'm doing sig figs, sorry. 137. That's how much carbon's in there. I can do the same thing for percent H. And there are 18 of those. And for that one, I got 6.1645%. And you can see how this is going to work out. So here's an N, 14.007. There's 2. For a decimal point, I got an answer that was really tiny. 9.5189. And I believe we've done enough examples of this, so I'm just going to punch in the last one in my calculator. And then similarly for oxygen, you get 27.181. And if you add all of those together, you should get 100%. I'll leave that as an exercise for the viewer. Again, my numbers on the board have fewer sig figs than they did on my slide right here. I did mean oxygen, you're right. That is a typo. Well, it's not really a typo if I wrote it. Good catch, thank you. Whoop, there we go. Everything is good. But you'll notice that my answers have fewer sig figs than the ones on this slide because, again, the periodic table that I was using when I created these slides is different than the one that I have in front of me right now. So your sig figs will vary based on your periodic table, so just be mindful of that. yeah, it's a righto. I make those all the time. This might be the picture. Yeah, here we go. So I drew a picture earlier today that looked like this. And so a diagram like this is representative of what happens when you decompose formulas or molecules into just samples. In the diagram shown here, I can see that the ratio of carbon to oxygen is 1 to 2. And so that will help us figure out the empirical formula through this analysis. And the reason that we have to do it this way is because it's not possible to grab a single atom or molecule and then analyze it that way. In some very rare cases, it is possible to do that, but a lot of the time stuff is reactive and it changes while you're examining it. For most compounds, it's just far easier to decompose stuff and then weigh it. Because weight at a large quantity being like at the gram scale as opposed to the microgram scale, is much more reliable in terms of figuring out what's going on, there being less experimental error. Now, because any formula that we use requires us to know the number of things that are in it, we can't use mass to work with that. So turning stuff into grams is only the first step. The most important thing that you can do is you can turn everything to moles when you're working with your quantities. So if you know how much stuff you have in terms of mass, turn it into grams, turn it into moles, and then you know how much quantity you have. From there, you can relate stuff to formulas, which would be using this example here. And these slides we talked about a little bit before, where I talked about the family that these molecules belong to. So for this molecule ratio on the screen here, I have about twice the number. I have X carbon and I'd have 2X oxygen. So the ratio must be 1 to 2. So anything that fits this ratio is okay. But anything that does not fit the ratio would not be okay. So this is not carbon monoxide in this sample. This is also not dicarbon monoxide. That can't be possible because the ratio just doesn't match up. When you do this sort of analysis, you get the empirical formula. So what we're going to do is we're going to do a little bit of work trying to figure out empirical formulas for substances using molar ratios. And your textbook has some fairly simple examples, so we're going to go over that right now. So let me just put a sample problem on the board, and I'll go over the general process on the PowerPoint, or not PowerPoint, but the Photoshop. And I didn't capture the entire problem. That's okay. All right. So the general gist for any empirical formula problem is the first step is to turn everything to moles. Because formulas are determined by knowing the ratio of their count, we need to turn into something that is a count. So we're going to turn everything into moles. Once I have everything in a count, we're going to determine the ratio, and I'm going to write this on the board. Pseudo formula. I don't know how to letters, apparently. Let me just try this word again. I'd love to blame the tablet, but I think that was an error between keyboard and chair. And then the last step is we're going to turn the pseudo formula into the empirical formula. So let's do this. So step 1, turn everything into moles. So I'm going to take my mass of carbon and my mass of hydrogen, and I'm going to turn them each into moles. So if I go grams of carbon, moles of carbon, grams of hydrogen, moles of hydrogen. There we go. I've turned everything into moles. All I got to do is put the numbers in. And so that just means going to the periodic table and grabbing those numbers. And when I do that, I get 1.17, 12.011. I get this many moles, 0.0974. And then down there, I get this number. So that was step 1, to figure out the number of moles. The step 2 is I'm going to make a pseudo formula. And the pseudo formula is as easy as this. Here's my carbon. Here's my hydrogen. There's my formula. C 0.0794, H 0.285. And all I did was just take these numbers and just put them right in there as subscripts. But no chemical formula that you've ever seen looks like that, right? So that's why this is called a pseudo formula. It's sort of a formula, but it's got some issues. We need to take care of those issues. Namely, that you can't have decimals or fractions or anything in the or in a formula. So the way that we get rid of those is how we would get rid of any fraction or do anything in the empirical formula. If I had a number that showed up in multiple places like this, and I wanted the empirical formula, I just divide by this. In the fraction, in order to get rid of this number, I'm going to turn this to 1 by dividing by the smaller of the two numbers. So 0.0974 is smaller than 0.285. So if I get this divided by this, I will end up with C1, because these are the same number. Now I'm just going to have whatever H ends up being, and we're just going to work from there. So 0.285, 0.0974. That is not as close to what I would have hoped it would have been. So I'm going to write this down. Did I write the right number down? I did. I'm just checking my calculation to make sure that I got the correct numbers here. Because one of those was a little bit further away than I'd like. I guess this is close enough to this number. Yeah, I'm getting CH3 as my answer. It's just that this was not as close as I would have liked it to be. Is that what my answer was on the previous slide? Yeah, it was. Okay. So in order to get the empirical formula, I had to take these and divide by the smallest number. And so I got that, 1 and 2.92. And then I said, oh, that's close enough to 3. I'm going to turn it into a 3. And then this is the empirical formula. For this calculation over here, I took these numbers and turned them all into moles, but I didn't do any adding. Okay, so I am treating these two things independently until I turn them into the pseudo formula. Can you round 2.92 to 3? I don't like to. So my intent was for the problem to get much closer to 3. Most of the time you're going to see stuff like this. And you're going to be like, okay, that's very obviously 3. Other times you're going to see stuff like this. And you're going to be like, what the heck do I do with that? And in both cases, we're going to have an option that you exercise every time. If you're really close, round to the nearest integer. If you're right on the halfway point, so for example, if you had something like this, then what you do is you times both things by 2, and then this is your empirical formula. So generally speaking, we're supposed to be multiplying by something to clear fractions. But because of experimental error and how few sig figs I have, I'm going to guess that's the reason why these numbers don't work out exactly right. Let's do another example. This example actually has a situation where we do have to do that. You got it. I didn't capture the problem. So we're going to do the exact same thing. And what that means is I need to do this. We're going to capture that, delete everything else, and then just paste this back in here. Just so we have it handy in case you want to follow along with that. All right, so step 1, turn everything to moles. Let's do that first. So we'll take grams of chlorine and moles of chlorine. In a mole of chlorine, there are 35.453. And I got 0.29955. I'm going to round that to 2996 for 4 sig figs. I can then turn oxygen into moles. type the number in my calculator, 15.999. And when I do that, I get this. Actually, let me leave that on the screen just in case you need it for a second. So I've turned everything to moles. Now I need to determine the ratio. So we will make a ratio out of these two things. So Cl 0.2996, O 1.050. In order to get rid of my pseudo fraction, or pseudo formula, I am going to divide by the smaller of the two numbers. So 0.2996 divided by itself becomes 1, but 1.050 divided by 0.2996. So I get CL1. I'm not going to write the 1, but I get O 3.504, which is really, really close to 3.5. So I need to choose a number to multiply by in order to clear out this fraction that would get me close enough to a whole number. And hopefully you're looking at that and determining that we need to multiply this by 2. Because 3.5 times 2 would be 7. So this is the empirical formula of our compound. Note that there is no number in there I can divide out. So sometimes your empirical formulas will have a non-1 number in every atom. So you don't always have to reduce down to 1. Sometimes like you'll have an even and an odd number, and that's the best you can do. So that is how we do empirical formula problems. Later on, what we're going to do is we are going to add this method alongside mass spectrometry so that we can figure out the molecular formula. I believe that's on the next slide. Oh, that's actually up here. I guess 2 slides away. So what I'm going to do is I'm going to put this problem on the board here. I multiplied by 2 because it was 3.5 and needed a whole number. That is correct. Yeah. So if I had a formula that was ClO 3.5, I can't have half an oxygen atom, so I had to double it. Remember that all we're getting from these sorts of analyses are like a pile of things, and there's 3.5 times as many O's as there are Cl's. So what I would then say is the ratio isn't 1 to 3.5 for its formula. The ratio must be 2 to 7. Yep, you got it. I'm going to put this problem on the board. We're not going to solve this today because we're out of time. It's already 1:55, and I did start a little, or it's 2:55. I did start a little bit early. So I'm going to leave these 2 problems for you to practice. I'll stick around for a few minutes to answer any questions before we go. But go ahead and copy that down. I will then put the title card back up in about a minute or so. I want to thank everybody for coming out to lecture today. We are 3 weeks in, which means that we're about halfway to the first exam, and I'm going to be spending this weekend writing some quizzes for you. I'm going to write quiz 2. That will hopefully be up later tonight or tomorrow. Your worksheet number 1 is due tonight. Make sure you get that in. I have seen that out of 70 or so students enrolled in my class, I have gotten about 25 of them turned in, so I'm expecting a lot more of them. Make sure you finish that up before the deadline, because once I hit download, if it's not in that pile, I won't have it. That would be bad. So make sure that you submit before it's too late. All right, again, thanks for coming out. I will see you next week. Have a wonderful weekend and stay healthy.